Hello physics students, and welcome to Candlelight Physics. Now I chose to do our studies today by candlelight for a lot of reasons. The first is that this turns out to be the very last lesson of our entire electricity and magnetism course. So we're kind of celebrating because you've done a lot of studying, you've studied a lot of difficult physics, a lot of difficult mathematics. And so, again, we're celebrating your tremendous achievement of getting through a very challenging course. Another reason we're celebrating is because today, we're finally going to get the full picture of this electromagnetic force. We studied electricity, we studied magnetism, and finally they'll be fully linked as the electromagnetic force. But another reason why we're studying by candlelight is because I want to basically take you back in time, in a sense, to the time when this theory was fully completed. It was completed by James Clerk Maxwell, a Scottish physicist, in 1865. Just to give you a sense of what 1865 was like, well, you already have a sense of that because that's right when the Civil War ended, the year Abraham Lincoln was assassinated. And so you already have a feeling for 1865. Maybe you've seen some movies about that time period. And as you know, technology was very limited back then. They had maybe some, devices like pocket watches, or they had like mills, water mills to cut logs or something. And that's about it. And lighting was candles and lanterns. And also writing was done by quills. So that's what we're going to do. We're going to be doing our physics just exactly how it was done back in 1865 by candlelight and with quill. So let's get started. All right, so take a moment to write the title, Maxwell's Equations, prominently in your notes. All right, so let's begin with the first law. Now, because writing with a quill takes so long, what I've done is I have begun already writing out the meanings, and what I'm just going to be doing is writing out the equations. So here we go. Already the ink is running. Not so easy to write with a quill. And you notice also how slow it is. I think people back in the 1800s had a lot more patience than we do. So here it is, E.dA equals Q enclosed over epsilon 0. And you may be thinking that this looks familiar, it looks like Gauss's law, and you would be correct. And so the meaning of this equation is that the net electric flux into or out of a closed three-dimensional surface is equal to the net charge enclosed divided by epsilon 0. Essentially, all I'm doing is reading that equation, what it says mathematically. And as we studied earlier in the year with Gauss's law, that what this means is that if you draw a 3D closed box, the box has to be closed. It has to trap off some space within it from the rest of space. Then the net electric flux shown here is negative because we have more electric field coming into the box than coming out. And that must mean that we've got a negative charge enclosed. So net negative charge enclosed. But I should point out, this is not the way Maxwell stated the law. The way he stated the law is actually like this. And this is going to look a little strange to you because there's going to be math symbols here that you haven't ever seen before. So, the quill sometimes does not like to wait. When the ink starts drying, you have problems. Let's see now. There we are. Now, this little triangle symbol is something that we have not seen before. It's a special symbol that's a three-dimensional derivative. And so what does that mean? Now, I'm going to talk a little bit about what this means, and I just want to explain that this is what you're responsible for in our curriculum. This is beyond our curriculum. I'm about to talk about calculus that's Calc 3. In other words, the typical science or math student doesn't learn about this until their sophomore or sometimes even junior year in college. So if what I'm going to say confuses you, it's okay. I am jumping ahead to something that you don't truly understand. But I want to talk a little bit about it because it gives Maxwell's equations more meaning. So when we have this triangle called the del operator, and we dot it with a vector, what it is it's like a vector derivative. And you could notice here ddx I hat, ddy j hat, ddz k hat. And we dot it to the electric field vector in this case that has x, y, and z components. Now, this dot product is like the dot product that we've been studying all along. Like, for example, in the work formula, work equals F dot D or FD cos theta. The dot product is not zero when the vectors are parallel to each other. In other words, I hat dot I hat is 1, but I hat dot j hat is 0, and I hat dot k hat is 0. So what we see when we dot this special kind of derivative to a particular vector, the x component, the x derivative gets dotted to the x component, and that's the only part that survives. But if I try and take the x derivative of the y component, the I dot j is 0, so I do not take the x derivative of the y, and I don't take the x derivative of the z. And the same thing goes for the y derivative. Notice when I dot j hat dot I hat, the y derivative does not apply to the x component of the vector. It applies to the y component, but not the z. And the same thing for the z derivative. It does not apply to x or y, it only applies to z. I could summarize that like this, that the divergence, this derivative of an electric field vector, is the x derivative applied to the x component, the y derivative applied to the y component, and the z applied to the z component. But what does that mean? What I'm going to do is show you through a visual. So here is a simplified version of what the divergence is. Imagine that I've got an x vector, maybe it's 10 units long, and then I apply an x derivative to that x vector. What that means is that I'm figuring out what happens to this vector, the x vector, when I take a step in the x direction. If it was 10 here, and then I take a step and then it's 12 here, then the divergence is 2. I went from 8 to 10, or 10 to 12, sorry. So that's 2, a positive 2. If the x vector is 10, and I take a step forward, and now it's 8, I went from 10 to 8, the divergence would be negative 2. So again, it's what happens to this vector when I step in its direction. What happens to the y vector when I step in the y direction? What happens to the z vector when I step in the z direction? So that's what a divergence is. So in other words, as I just showed you, what the divergence is the change a vector undergoes as a step is made in the direction of the vector. As you step in the x direction, how does the x component change? As you step in the y direction, how does the y component change? And as you step in the z direction, how does the z component change? So if you want to copy this down, go ahead. But again, it's not necessary. This is far beyond our course. But if this sort of thing interests you, then go ahead and copy this and leave space for the other kind of derivative, the curl, which I'm going to talk about later. Let me show you with another example. Here is a vector field, and you can see that at this particular y component, all of these vectors are the same size. And as I move up, they're all the same size, but they get bigger and bigger as I move up in the y direction here. This vector field has a divergence. In other words, as I step in the direction of the vector changes. It increases or decreases. And so there is a non-zero divergence to this vector field. Now, how does that apply to Gauss's law, or our first of the Maxwell's equations? Well, if you look at this, if I'm stepping in the direction of the electric field, you see there's a change here. In fact, there's a negative change. This vector maybe went from 10 down to 2, so the change is -8 as I stepped through this x-coordinate. And because that step, the change was negative, that means that the divergence is negative, and therefore there must be a negative rho, a negative charge density, negative charge in that box. So this is another more elegant, more general way, more useful way to express this same idea. This is more of the form that Maxwell expressed. So that's equation 1. Let's move on to the second equation. Let's see if my quill is going to work after all this waiting. All right, so what it is, well, let me write it out and then you'll see. Okay. Oh, I messed up. I knew this was going to happen because the quill is not very forgiving. Murphy's Law. Well, BDA. That's a DA again. Now, you should recognize this and see that it looks essentially like Gauss's law, but for the magnetic field. And what it's saying is that rather than EdA, the electric flux being equal to Q enclosed over epsilon 0, the magnetic flux through any closed surface is always 0. The meaning of this, well, I kind of said it already, the net magnetic flux into or out of a closed three-dimensional surface is always 0 everywhere in the universe. Another way to say what this means is that all magnets have 2 equal poles. Yet another way to say what this means is that magnetic monopoles do not exist. So if I take a bar magnet here with a north and south pole, the magnetic field comes out of the north and goes into the south, as you can see. If I draw a three-dimensional closed surface, you see that magnetic field lines come out. I've got positive magnetic flux on this side, but on this side, I have negative because the magnetic field lines are going in. And so the net magnetic flux into or out of this area is always 0. Same for a wire that has current going around it. The magnetic field lines go around in a circle like this. Again, if I draw a closed three-dimensional shape, I've got negative magnetic flux coming in here, positive coming out there, canceling out no net magnetic flux. And another thing that's, as I said, you cannot have a monopole, just a north or just a south pole of a magnet. It cannot be in nature. For example, if I had just a north pole and no south pole to an object, I would have positive magnetic flux. So you could have monopoles with charge, like a proton or electron, but you cannot have monopoles with magnetism. Now we could state that in this form by just writing the same del operator applied to the magnetic field. And it says the same thing as that equation. So copy these into your notes because, again, this and this are definitely part of the curriculum. If you want to skip over these, you're welcome to. Only if you have interest. You know what? Go ahead and put them in your notes just so they're there. Why not? Okay, so 2 equations. We've got 2 more to go. So I realize I'm waving a paper towel into view. That's not historically appropriate, so I apologize for that. Okay, here we go. 2 more. All right, so the next equation. Get the quill ready. Okay, so you may recognize this because it looks like Ampere's law. I mean, not Ampere's law, Faraday's law. The only difference is in class we put an EMF here. Voltage is the change in magnetic flux per time through an area, but voltage is the electric field integrated around a path. So we went over this earlier in the year. So here's the meaning. Basically, you're just reading what this equation says. A changing magnetic flux through a 2-dimensional surface causes an electric field that runs along the perimeter of that surface. So an example, if I had a magnetic field going through this area and it decreases, then what happens is we get a voltage by Lenz's law that we need a B induced coming out of the paper here, and by the right-hand rule, the voltage the current in a loop would go this way. In other words, the electric field goes around this way. So essentially, a changing magnetic field creates an electric field. Inside of a solenoid, of course, we studied that without a wire loop, even without a wire loop, in the space inside of a solenoid, that electric field is formed. So in other words, I'm getting ahead of myself here. So let me next write down the calculus way, the 3-dimensional calculus way to express this idea. So instead of the divergence, we have now another kind of 3-dimensional derivative, that same del operator, but cross product to the electric field. Let's see. So there's the same idea but expressed more in the way that Maxwell would have, or that college physics courses expressed this equation. But what does this mean now with the cross product to that del operator? So let me all right, gotta get my sheets here. Here we are. So the curl is like that derivative operator crossed to the electric field. So here's that del operator. It has an x derivative, x direction, y derivative, y direction, z derivative, z direction, and we cross it to the electric field. Now remember, the cross product with vectors was like the magnetic field, or magnetic force was qvb sine theta, or q velocity cross magnetic field. And the cross product for vectors is non-zero when the vectors are perpendicular to each other, but zero when the vectors are parallel to each other. The opposite of this, the dot product is 1 when the vectors are in the same direction. The dot product between two components, is not 0 when they're perpendicular to each other. In other words, when I apply this x derivative to the x component of the vector, I hat cross I hat is 0. So the x derivative does not apply to the x component. I hat cross j hat and cross k hat is non-zero, so the x derivative is applying to the y component of the field and the z component of the field. Similarly, the y derivative doesn't apply to the y direction. It applies to the x component and the z derivative applies to the x and the y. Now, if I were to express this only for the x derivative, as I just said, I would take the x derivative of the y component, I cross j, and then the x derivative of the z component, I hat cross k hat, which if you do the right-hand rule is positive k hat, and this is negative j hat. But then I would have to do that cross product for the y derivative to all three of these. So I'd have a lot of terms here. In fact, 9 of them, and some of them would be 0. But what does that mean? That I'm taking the x derivative of the y component and the x derivative of the z component, but not the x derivative of the x component. So let me show you, but first let me reconfigure the camera. So this is what a curl is. I'm applying a derivative, like an x derivative, to both the y and the z, but I'm not applying the x derivative to the x component of a vector. So what it means is I'm asking what's happening, for example, to the x component, not when I step with x, but when I step in y. And so what it means conceptually is what happens to a vector field as you step sideways, not forward. That's the divergence. Curl is what's happening to this when I step this way. What's happening to this when I step that way. So it's the change. Like let's suppose I have 10 and then I step this way and I have 12. The curl is from 10 to 12, positive 2, and it also has a direction, more information than we need for right now. If I have 10 and then I step sideways and it becomes 8, I went from 10 to 8, I have a curl of negative 2, and there's also a direction to that. So that's what a curl is. What happens to a vector when you step sideways? Divergence is what happens to a vector when you step forward. So in words here, the change, what the curl is, this special kind of derivative with a cross product instead of a dot product, it's the change a vector undergoes as a step is made perpendicular to the direction of the vector. Move in the x direction, what happens to y? Move in the x direction, what happens to z? Not move in the x direction, what happens to the x? So how does that then apply? Oh, before I do that, if you want to copy the rest of this down, only if you're interested, go ahead and copy this down now. All right, so let me show you an example of a vector field that has a curl but not a divergence. Now, in college, when you study the curl, what the professors like to say is that a field that has a curl swirls around like a tornado. And I don't like that because that's not true. There are some fields that swirl that actually don't have a curl. Again, it's what the curl is as you step sideways does the vector change. Not when you step forward does the vector change, but as you step sideways. See here, if I step forward in the direction of the vector for any x coordinate, the vectors don't change as I'm moving in the direction of the vector. But as I step sideways, see the vector's going that way, I step sideways and the vector changes as I'm stepping sideways. That means the vector field has a curl, not a divergence. Curl, yes, no divergence. How does that apply? Oh, and if you want to copy that, go ahead. Again, this is extra, you don't have to. All right, well, how does that apply to Maxwell's equation or the magnetic field? If you see here, this is the electric field inside of a solenoid where a magnetic field is changing. In this case, the magnetic field would be decreasing, and so we would have, by Lenz's law, the electric field going that way. Now, as you can see, if I step forward with the vector, it's not really changing. But notice as I step sideways, I am definitely getting a changing vector. See that? I go like this and I have a changing vector. And that means, again, stepping sideways, there's a change in the electric field. Why? Because the magnetic field is changing. So that's how the magnetic field can create an electric field. As it changes, it creates a curl to the electric field. All right, now, the last of Maxwell's equations. So let me write it out. Let me take my time so I don't mess up like I did last time. All right. At this point, you might be saying, wait a minute, that's Ampere's law. So far, all of the equations we've seen today are equations that we've already seen. Gauss's law for electric field, Gauss's law for magnetic field, and Faraday's law. Why are we calling these Maxwell's equations? And this is Ampere's law, of course. If all of them were thought by other physicists already. The reason why is because Maxwell discovered a missing piece. This is what he added. And there it is, our final equation. Now, let's first just talk about the meaning. So, again, you could just look at and see the meaning right in this equation. That the magnetic field around a closed loop, that's what that little circle means, integrated around a closed loop is caused by 1, the current that passes through the surface bounded by the loop. That's this part. What we already studied in the magnetism topic as Ampere's law, as I already said. But it's also caused by changing electric flux through the said surface. So to get magnetic field, you could either have current or you could have changing electric flux. Now, to talk more about what this means and why it's so important, and also to talk about why it's so significant, this one term, I'm going to write this out in the three-dimensional calculus form that we've been working with. So here it is. The curl of B is current density, like the current, but current density on a smaller form, plus oh, I meant to just write the vector sign over the E. Messed up again. By the way, these are what are called partial derivatives. They're just derivatives. Think of them as derivatives for now. So there is, I guess I boxed that one in. Let me box this one in. All right, so if you want to take a moment to write this down, well, definitely write this down, and these are the 4 Maxwell's equations for today. So do that now. All right, what does this expression mean? Similar to this, that a magnetic field around the curl of B, again, as you step sideways, there's a change in the magnetic field as you're moving sideways, and that change as you move sideways is caused by either current density or current, or a changing electric field. See, that's what Maxwell discovered, that an electric field also causes a magnetic field. A magnetic field causes an electric field, and he discovered that also the other way around, an electric field causes a magnetic field. Now, how did Maxwell think of that? Again, this is not part of the curriculum, but only if you're interested. Maxwell's thought process. Here it is. I realize that we're not all on one page. I think it's okay. I think it'll fit. So Maxwell's thought process. So what he did is he imagined a simple, very simple circuit with a voltage source, EMF, a switch, a resistor, and a capacitor here. So this is like a parallel plate capacitor. When this switch closes down, what happens is current will be going in this circuit like this. And without the capacitor here, we would have, according to Maxwell's Ampere's law, we would have a magnetic field created by the current by the right-hand rule. So we'd have magnetic field coming out of the paper as the current's going like this, like it's coming out of the paper. But if you put a capacitor here, in this region, if I draw an Amperian loop, which is what this oval is, like a circle, there's no current through that Amperian loop. And so, if this were the end of the story for this equation, this concept of magnetism, there's no I enclosed in that loop, and therefore there's no magnetic field around that loop. But here's the problem. Because now all of a sudden, as I'm stepping sideways, the B is coming straight out of the paper, and as I move sideways and I go from, there's no curl, there's no change in the magnetic field as I'm stepping sideways. The curl is 0. Okay, that's good because we don't have any current anywhere in these points in space, so there shouldn't be a curl. But when I get to this point, once I step to the side here, suddenly I've got a curl that's non-zero. I went from magnetic field, make up a number, 10, to magnetic field 0. That's a change in the sidestepping direction. But where is the current here? Because if there's a curl, and that's the end of the story, there must be a current wherever there's that curl. And there is no current right here. It's just the edge of the capacitor. And so, or even if the capacitor ended, not even that. So Maxwell said either this is wrong as it is, or there's a missing piece. And he opted for there being a missing piece. And then he thought, well, okay, so I just concluded that there cannot be a curl in the magnetic field. There must be magnetic field here just the same as there was all along here and here. So there's the same magnetic field here. So what is going through this Amperian loop if it's not current? What's happening is as the current is flowing, this plate is becoming positive and this negative in the capacitor. And what's happening is we went from 0 electric field to suddenly an electric field that's increasing as the charge is increasing. So Maxwell said, there's an electric field that's changing in that Amperian loop. It's not current that's causing that BDS, it's a changing electric flux. And so he concludes that curl of B must be 0. There must be the same magnetic field here. In other words, there's a B in this capacitor. And so the new problem is that there's no current through the capacitor, so he added this new term. And there's a way to derive this. If you watch the videos that the College Board has published, one of the presenters derives this. Again, this is already way beyond what we need to know, so we're certainly not going to derive it. It's the beauty of the concept, understanding how there cannot be a curl here because there's no current. That's what I think is the most beautiful part of this little thought experiment of Maxwell's. So if you're interested, again, you could go ahead and copy this down. If you feel that it's too much, skip it, no problem. I don't take offense. You're not going to lose any points. You're not going to get any questions wrong on any test this year. So go ahead and copy if you're interested. Now, right about now, you may be wondering, if Gauss thought of this equation, Faraday thought of this concept, and Ampere thought of this equation, is it really fair to call this entire theory Maxwell's equations simply because Maxwell thought of this one term here? And the answer, according to physicists, is a resounding yes. So let me explain some of the practical consequences of Maxwell's theory. So right from the start, Maxwell discovered or realized that his theory answered an age-old question, a centuries-old question that had been bothering physicists. Specifically, what was light? And Maxwell finally understood that light was nothing more than vibrating electric and magnetic fields. So here you can see that I have electric fields in this direction and magnetic fields in this direction. Furthermore, if I were to trace a line through the tips of these arrows, you would see that I'd be drawing out a sine curve for the electric field. And the same for the magnetic field. If I were to draw a line or a curve through the tips of the arrows, I'd be drawing a sine curve, but perpendicular to this sine curve here going this way versus that way. So what do Maxwell's equations say about these electric and magnetic fields? Well, maybe we'll start with this expression. What it says is if there's a curl in the magnetic field, then something must be happening to the electric field. Well, is there a curl in the magnetic field? Remember, a curl is what happens to a vector when you step sideways. So imagine here, I'm looking at this vector here, I'm standing here, and I see this is the magnetic field going in this direction. And I step sideways, and I see that, yes, indeed, the magnetic field arrow here got shorter. So there is a curl because I stepped sideways in the direction of the velocity and the magnetic field changed. In other words, it decreased. Furthermore, we could use the right-hand rule and imagine a little Amperian loop here, and we'd get a positive answer if we integrated around our Amperian loop in this direction. In other words, the curl is positive in this direction, in the upward direction. So there's a curl because of these two vectors pointing up like this. Now, this equation says that because there's a curl, there must be a changing electric field. In other words, dE dt must be increasing. The electric field must be increasing in this direction because of that curl. And is that really happening? Well, if this is a traveling wave moving this way, well, imagine this is a water wave and you're floating on a little inner tube here. As this crest approaches, you will rise up in this direction. So that tells us that this electric field, this crest of the electric field is approaching this point. This arrow is increasing. What about the electric field? What does that say about the magnetic field? Well, if you look at this expression, you see that the electric field also has a curl to it. In other words, if I step sideways to the electric field at this point, say, if I step sideways, I see there's a change in the electric field. There is indeed a curl. If you use the right-hand rule, you see that the curl would actually, if you made a little Amperian loop here, the curl would be this way. But because of the minus sign, if I bring it to this side, then I would be saying that the magnetic field must be increasing in this direction. Is this arrow increasing? Well, yes, because if this is the crest of a wave approaching this point, you see that the crest is approaching. Something floating in the horizontal direction here would be rising as this crest is approaching. So you can see that there is a changing electric field with respect to time because there's a spatial variance in the magnetic field. There's a curl in the magnetic field. That means the electric field has to be increasing with respect to time. Because there's a spatial change in the electric field, there must be a time change in the magnetic field. And these two principles play out throughout this line segment so that the electric and magnetic fields are vibrating. It's like crests and troughs of a wave that move in the forward direction. So Maxwell finally answered, what exactly is light? Something that, as I said, physicists had been puzzling over for centuries. But it wasn't just physicists puzzling over the question of what light was. Think about humans going all the way back to the caveman era. So hundreds of thousands of years, people were looking at the sun, looking at the stars, looking at the moon, and making all kinds of theories, theological stories about what the stars were, what the sun was, what the moon was. So Maxwell literally was the first person in hundreds of thousands of years of human history that finally understood what light was. Tremendous achievement just with that one understanding. But it wasn't long before people realized that you could make a wave like this if you just took a wire and you vibrated the electrons in that wire, because there would be an electric field that wiggled and a magnetic field that wiggled as the current was oscillating. It would create these waves of electric and magnetic fields. So the first person that I know of who was able to use that concept for practical means was Nikola Tesla in 1898. Tesla remarkably made a remote control boat in the 1800s. Again, imagine horse and buggy, very primitive kind of life compared to our standards. And Tesla made a remote control boat that responded at a distance. As time went on, people found other applications for these vibrating electric and magnetic fields. Eventually, they invented radio communication, and you think about how that changed history. Radio made politicians rise, other politicians fall when they could communicate through radio. It changed human history. War communications, it changed war. Well, you remember the story, no doubt, of Paul Revere. He sees the British coming, and then he's got to race on his horse to communicate that knowledge to everyone. Well, think about executing a war in that time period. If you were fighting, your troops were fighting hundreds of miles away, you had to tell someone to race on horseback to give an order. Maybe by the time they got there, weeks later, the war was over, right? So, but now through creating electric and magnetic field vibrations, radio communications, war changed dramatically, human history changed dramatically. Then, of course, you can think about radar. That also changed the history of warfare and human history. Television. Think about all the cultural changes that came about because of television. So now you had a TV station transmitting these electric and magnetic fields, and people could see images on a TV, how that changed culture and even politics. And then even think about this, space travel. Think about, we kind of take it for granted. A rocket goes into outer space. How do we direct it? How do we send data back and forth? All because of vibrating and electric and magnetic fields, because of these two equations here. And then just in general, more widespread wireless communication. Think in your house, you got a wireless router so you can send signals from room to room. Think about your cell phone. That goes even farther. Your cell phone sends a signal to a tower miles away. The tower then sends the signal to another cell phone. And maybe you send a text to someone, or maybe the tower sends you back a Netflix movie and you could watch a movie. So think about the cultural change that has occurred because of this vibrating and electric magnetic fields. And also live coverage of events. We take that for granted. But when there were the Olympics in China, how were people able to watch that live? Well, there was a broadcasting station that sent the signal to a satellite, beamed it to other satellites, and eventually another satellite beamed it back to the United States, and we could watch live Olympic coverage. So this has changed. Even today, it's continuing to change human society on a personal level and on a historical level. So this revolution that Maxwell wrote down in 1865, these equations, it's still not over. Where does this end, this electromagnetic technology? You can only imagine, and probably your imagination is even insufficient. So one thing I want to just close with is a quote from Albert Einstein, summarizing very nicely, very poetically, what this meant for human history. Albert Einstein said, "One scientific epoch ended, and another began with James Clerk Maxwell." So he was that important. Even someone like Albert Einstein realizes that human history changed in 1865 when Maxwell discovered this one term. So there they are, Maxwell's equations. Now, before I wrap it up, I just want to say a couple remarks again to remind you that a lot of the high-end math that I showed you is not on the AP, and it will not be on our physics tests, and it will not be on our physics final. All that stuff about three-dimensional calculus, the divergence and the curl, that's mathematics that you won't really see until maybe your sophomore year in college when you take Calculus 3. So if that stuff made you nervous, just completely disregard it. Basically, I wanted to show you the full scope of Maxwell's equations and the full depth of the beautiful mathematics just in the conceptual form. But again, if it didn't add to your understanding, and it made you nervous, disregard that. What you should focus in on are just the four equations that I wrote in their integral form, just how we express Gauss's law, the closed integral of EdA equals Q enclosed over epsilon 0. Those four equations written in that form. And then on the AP, all that you're responsible for is correctly interpreting them. So those sentences that I had where I said meaning, go back and look at those and make sure you understand the meanings of all the equations. But really, you don't even need those sentences, because at this point, you should just be able to look right at the expression, the math expression, and interpret it, because you have a great understanding of high school level calculus at this point, or even freshman college level calculus. So that's it. We have completed the entire picture of electricity and magnetism, the electric field, the magnetic field linking together in this beautiful force, the electromagnetic force. So I would say see you in the next physics video, but there aren't any more physics videos except for some review stuff we're going to be doing in class. So I'll just say I hope you enjoyed the course, and I hope you take physics again later in life in some other course, and I hope you enjoy that course as much as I know you enjoyed this course. So farewell. Thank you for joining me for a great year.